Hi everyone, welcome to EEE 137. This is week number 8, problem number 1, Al's experiment. Al performs an experiment comprising a series of independent trials. On each trial, he simultaneously flips a set of 3 fair coins. Okay, so for the first item, given that Al has just had a trial with 3 tails, what is the probability that both of the next 2 trials will also have this result? So let us first uh, denote each trial as x sub k. Okay. So for example, for the first trial, the outcome was there were 3 tails. Okay. In this problem, right? The first trial here is 3 tails. What is the probability that x2 and x3 has the same result as x1 given that x1 just had 3 tails? So the expression that we want to find here is what is the probability that x2 is equal to 3 tails and x3 is equal to 3 tails given that x1 is equal to 3 tails. Okay? So, this is an example of a Bernoulli process. So, once again, we review the Bernoulli process. For us to have a Bernoulli process, there is our time variable here is discrete, right? Because we have a discrete number of trials in this case. Okay? The time is not continuous. It is discrete. And then each trial, the probability of arrival of a success is constant because the number of coins does not change over the whole experiment, and we still have a fair coin in this case, or fair coins in this case. And another thing is that there must only be 2 outcomes in this case. So the outcomes that we define here is either we call the Bernoulli trial as a success if we obtain 3 tails, otherwise it is a failure. So in this case, if the first trial has had a success, what is the probability that the next 2 trials will also have a success in this case? And one of the most important property of Bernoulli processes is that we have an independent arrival times or inter-arrival times in this case. What does that mean? That means that whatever has happened in the past does not affect your present outcome. Okay? So, whatever will happen in x2 is not affected by what happened in x1. And at the same time, what happened in x3 is not affected by what happened in x2 and is not affected by what happens in x1. In other words, each trial are independent of each other. Or, in other terms here, we have a memoryless random process, or we have a fresh start property. For every trial that we have a fresh start. Okay? And this one is equal to probability that x2 is equal to 3 tails and x3 is equal to 3 tails, because this outcome, okay, this one is independent of this one. Therefore, we can simplify the probability expression into this result. And once again, these two events are independent of each other. Therefore, we can multiply their probabilities. Okay? And what is the probability of these 2 events happening? Okay? This is equal to, what is the probability that a trial will have 3 tails? Okay? So, if you have 3 fair coins, the number of trials in our sample space is 8 outcomes, because 2 to the 3. And then, for us to have 3 tails, it is our desired number of outcomes is only 1. We have 3 tails. So, the probability of this happening is 1/8. And the same thing with here. So, this is also equal to 1/8. Therefore, our answer in number 1 is 1/64. Okay? How about item number 2? So, whenever all 3 coins land on the same side in any given trial, Al calls the trial a success. We have another Bernoulli process in this case, but we redefine the success in this case. We have a success if we have 3 heads in those 3 fair coins that was flipped, or 3 tails. And we define what is the probability of success in our new Bernoulli process. So in item number 2, the probability of success, we denote that as P. Okay, P is equal to 2 over 8. Once again, the sample space that we have is 8 possible outcomes, and then we only have 2 desired outcomes. Okay, either they are all heads or they are all tails. Simplifying it, we have probability of success equal to 1/4. Okay, so what are we trying to find here? Find the PMF for K, the number of trials up to but not including the second success. Okay, so what we have here is we want to find the probability distribution or probability mass function of the number of trials K up to but not including the second success. That just means that we have the probability, the event here of within K trials, right? We have one success only. Okay? And then the probability that on the K plus 1 trial, we have our second success. Right? So that is what we are trying to find here. Right? Because we want to find the PMF of K, wherein we have the number of, where K is the number of trials before the second success. Okay? And that will only happen if out of the K trials that we have, we only have one success. And on the K plus 1 trial, that means the next trial after those K trials, we have our second success. So, we know this one, probability that K plus 1 trial, we have our second success, that is just equal to, P, the probability of success. This one, 1 over 4. And then this one, we can solve this. We have a PMF here. We can define this as a binomial random process or binomial random variable. Because we have a fixed number of trials, that is K, and then we define one success out of those K in that K number of trials. Okay? So recall, when we want to get the probability that we have one success within K trials, that is equal to K choose 1 times probability of success 1 times probability of failure, okay, K minus 1. That is this one, right? So we only have one success and we have K minus 1 failures. And then we have K plus 1 combinations of all of those events, right? And then finally we multiply P here because we have this second event that we must have for us to have the second success at the K plus 1 trial. So this is equal to K choose 1. Simplifying, we have P raised to 2, 1 minus P raised to K minus 1. Right? So that is our probability distribution function. Where K here is, what are the possible number of success? K greater than equal to 1. Because equal to 1 because we can have only one number of trial before the second success. That means on the first trial we have success, on the second trial we have our second success. And then it is possible, we have possibilities that it can go up to infinity, but that is nearly impossible already. So this is our probability mass function for the second problem. Okay? So that's it for this problem. See you on the next video.